Okay, so let me start with the abstract definition of a group. So what is a group? Let's call it G. It's a set along with some binary operation that takes us back to the group. So we have some operation that takes us from G times G back to the group itself. So if we have two elements of G, G1 and G2, the product G1 times G2 should be a third element, G3, belonging to the same group. Multiplication for a group should satisfy three properties. It should be associative. We should have an identity element in our group that we usually write as E. And for every element in the group, its inverse should also be an element of the same group. So if G is an element of the group, we should also have an inverse G such that G times G inverse is equal to the identity. We have two kinds of groups. We've got finite and infinite groups. Finite groups have a finite number of elements, whereas infinite groups have an infinite number of elements. So I'm going to start with finite groups today with some basic examples, and then we will move to infinite groups for the rest of the time today. And then on Tuesday, I guess we will be focusing on the Lorentz and Poincaré groups. So let's start with finite groups. An example of where you see finite groups in physics is, for example, when you're looking at lattices and you're considering the symmetries of the lattice, rotations, reflections around lattices. All these groups are finite. For example, to make this simple, let's take a triangle. And let's label the vertices of this triangle as 1, 2, and 3. What are the symmetries of this triangle? If I allow myself to only do rotations on this plane, but stay on the plane, what I can do is I can move vertex number 1 to vertex number 2, vertex number 2 to 3, and 3 to 1. So I can take 1 to 2, 2 to 3, and 3 to 1. This is one rotation. I can apply the same rotation twice, and that will take 1 to 3, 3 to 2, and 2 to 1. And if I apply the same rotation once more, I will go back to where I started. So this is actually what is known as C3, the cyclic group with 3 elements. And so if I call the first rotation, I write it abstractly as A. The second rotation will be A squared because I apply A twice. And A cubed will take me back to the identity. To write this thing in a better way, I could write this element of the group as 1 going to 2, 2 going to 3, and 3 going to 1. This can also be written in this form, 1, 2, 3, which means that 1 goes to 2, 2 goes to 3, and 3 goes to 1. And this is equivalent to A in the cyclic group. How about the second rotation? This takes 1 to 3. It takes 2 to 1. And it takes 3 to 2. So in this notation, that would be 1 going to 3, 3 going to 2, and 2 going to 1. And this is called the cyclic notation. This is a cycle because the elements here permutate in a cyclic way. Now, what if we not only allow rotations in the plane, but we also allow reflections around the 3 axes of symmetry of the triangle?
If you were to rotate in the opposite sense,
then it's the same thing. These are the only 3 elements of the group. So yes, let me say why this is a group. Thank you. It satisfies, first of all, multiplication of any 2 elements still stays within the group, right? And then it is easy to see that it is associative. If you do a rotation, let's call it G1, a rotation G2, and a rotation G3, the rule of association is true. You can check that. We have an identity, which is just to rotate by 360 degrees. And we also have an inverse for every rotation. The inverse of 1, 2, 3 would be 1, 3, 2. Okay, what if we also allow reflections? Then reflection around this axis will just exchange the vertices 1 and 2. And I can write this element as 1, 2. Vertex 3 stays the same, so I don't need to write it here. I could write 3, but usually we omit it. If I take a reflection around this axis, then I exchange 1 with 3, and around this one I exchange 2 with 3. So that brings in 2 more elements, 1, 3, and 2, 3. Yeah? So if we combine rotations and reflections, we will have a group that consists of the identity, then the 2 other cyclic permutations, 1, 2, 3, and 1, 3, 2, and the 3 reflections, 1, 2, 1, 3, and 2, 3. And this is the complete group of permutations of 3 elements, which we denote as S3. Okay? The only way you can, the only permutations you can take of 3 elements are this. This group has, since we're considering permutation, it has 6 elements. Right? Okay. Now, what if we add one more element to our problem, and we consider permutations of 4 objects, or we consider the symmetries of the square? One, two, three, 4. Okay. Rotations in this case will give me these elements. 1 going to 2, 2 going to 3, and 3 going to 4. And if I apply this twice, I'll get 1 going to 3, and then 3 goes to what? To 1. So I can close this cycle here. Okay? And I can open a new cycle because 2 will go to 4 and 4 will go to 2. In this notation, this rotation would be written 1 goes to 3, 2 goes to 4, 3 goes to 1, and 4 goes to 2. But obviously, this is a much more compact notation. Okay, what if I take a third rotation? Now, 1 will go to 4, 4 will go to 3, and 3 will go to 2. And if I apply the same rotation once more, I will return where I started from, and this is the identity element. So this is the cyclic group for 4 elements. If we also include reflections, you'll see that we have 4 axes of symmetry for the square. This is 1, 2, 3, 4. So I'm not going to write now all the reflections that we get for the square. But you can check that we do not, even if we include rotations and reflections, we do not get the full group of permutations of 4 elements, which is S4, and has 4 factorial 24 elements. So S4 would be all permutations of 4 elements. But you can check that if we include rotations and reflections, we will only get a subgroup of S4. A subgroup, by definition, is just a subset of a group that is a group itself. Right? So the general group of permutations of n elements. Where are they? You can just not picture them as symmetries of the square. For example, one other permutation you can make of 1, 2, 3, and 4 is just to exchange, for example, 1 and 2. But there is no way that you can turn around your square on the plane or even in 3 dimensions, so that from this shape you go to 2, 1, 3, 4. Okay? You cannot visualize it like this. The group of permutations of n elements is known as Sn. And the reason why we care so much about these permutation groups is that there is a theorem I think it was Cayley in 1854 who stated this, that every finite group of order n and I didn't really define the order of a group, but it's the number of elements inside the group, is isomorphic to a subgroup of Sn. And you remember yesterday we talked about homomorphisms and isomorphisms for algebras? Well, these definitions are exactly the same for groups. So Sn is of order n factorial. You can find a subgroup of Sn that will be of order n, so that is isomorphic to your group. And of course, you can also state this as every finite group of order n is homomorphic to Sn, right? Okay. So in that notation, in this notation, we would write the general element of Sn as 1, 2, 3, and going to S1, S2, S3, Sn. Right? 1 would go to some number, 2 to some other number, etc. And according to what these numbers are, we can also write an element using the cyclic notation. Let me define what conjugate elements are. So if we take 2 elements of a group, And we can find a third element of the group, let's call it A, such that G1 can be written A, G2, A inverse. Then we say that G1 and G2 are conjugate elements. So an interesting thing about permutation groups is that conjugate elements always have the same cycle structure. And I will try to explain this. So let me keep this here. So say we take two elements of Sn, T and S. And S has a specific cycle structure. So what I want to show is that this element of the group has the same cycle structure as S. Why is this true? Let's start, for example, from number 1. So the question is, what is TS, T inverse of 1? Well, 1 can definitely be also written as T of some other number. Let's call it I. Yeah? So TS, T inverse of 1 is, let me not rewrite it. It's just TS, T inverse of Ti, which is just TS of the element I. So this thing, TS, T inverse, takes us from T of I to T of S of I. How about T of S of I? Using the same rule, this will take us to T of S of I. And so on. When will this cycle close? When S of I goes back to I. So this cycle, which is a cycle for TS, T inverse, will close at exactly the same number of steps that a cycle for S will close. Does this make sense? No? What is T of I? Okay. In this notation, when T acts on any element I is any number between 1 and n, T, which is some element of Sn, takes I to T of I will be some number. It has to be some number, because these are permutations. Whatever T is, there must be a number I such that T of I is 1. Okay, so let me give another example. Sorry, can you repeat again from the beginning?
I mean, can I understand it this way? We just regard the group elements as sum operation, and the sum, some kind of coordinates, and by doing the conjugate, by finding the conjugate elements of the group of G, it is the same as we do a coordinate transformation.
You can think of it this way, because when you do a basis transformation, you use these similarity transformations, which are a similar thing. Yes. But I should have been more clear about the cycle structure. So by cycle structure, I mean how many cycles does each element of the permutation group have, and how many elements do we have in each cycle? So let me write down a few examples, and I think it will be clear. If what I'm saying is that basically, if for S is whatever, if we take whatever other element of T and multiply them like this, then this thing will have the same cycle structure.
This depends on the fact that T of I is 1.
No, I can do it for any element. Let me start from an element J. Yeah? I know that this is T of some I. It might even be T of itself. I don't know. Okay? So this is J. And by applying TS T inverse on J, we are taken to T of S of I. Now, apply the same thing again here. Just replace I with S of I. This should take you to T of S of S of I. And this thing will stop when S, let's say, I don't know, S of S of S, S of S of S of I is, if this is I again, then we are taken back to
I was just not sure
T of I.
I mean, so when you act with TS, the inverse on some element, I wasn't sure if it has to be the same element or not as the one that you actually teach us. I know.
I'm applying this on a general element, but I'm using the fact that I can definitely write this as T of some element. Now, let me just write a few examples about cyclic notation and cyclic structures. So let's take an example from S5. 1, 2, 3, 4, 5. And let me say that 1 will go to 5. Let's try this one. 5, 4, 3, 2, 1. So let's try to write this in cycles. I always start with 1. 1 goes to 5. And then 5 goes to 1. So this cycle has to close here. How about 2? 2 goes to 4. And 4 goes to 2. So this cycle also closes here. 3 remains invariant, so I don't need to write it there. How about another element of S5? Okay, what's happening here? No, wait a second. I don't want this. Okay, let's assume that 1 goes back to itself, so I don't need to write it. I'm going to start with 2. And then I just have a cycle with 2, 3, 4, 5. Now, what I mean by cyclic structure is that these two elements have different cyclic structures. This thing has 4 elements permutating cyclically, I don't know, circularly. Whereas here we have the exchange of 2 elements and the exchange of other 2 elements. So I can write this in general. This would be a cycle of A, B, C, D. And this, for example, would be A, B, C, D. So what are all the, for example, for S4?
So if you have 1, 4, and let's say 3, 2, is it the same cyclic structure as the first one? Or?
Yeah, that would be 1, 4, 3, 2. It's the same cyclic structure.
So it's only the number of related?
Only the number of elements in each cycle and the number of cycles. For example, what are the different kinds of cyclic structures we can have for S4? We have 4 elements, so we can either have all the elements in one cycle, or we can have 3 elements in a cycle and the 4th element remaining invariant. Or we can have 2 cycles of 2 elements each. Or we can have just two elements in a cycle and then the 2 other elements remaining invariant. Or we have no change and this is the identity. These are all the different types of cycles that S4 can have. Now, all the elements that are conjugate to each other are said to belong to the same conjugacy class. So in fact, these are the different conjugacy classes of S4. So as I said, the reason why these permutation groups are important is because they are homomorphic to any finite group. Sorry.
Anna, could you please explain the last part of the proof?
That proof with the
Yeah.
conjugate elements?
Yeah.
Yeah? Okay. Okay, so we start from a general element J. We can write it as T of some other element or of some element. So if I start from J and apply T S T minus 1 to it, I will go to T of S of I. T of I goes to T of S of I. So that once I apply the same transformation once again, I'm taken to T of S of I. Is this clear up to here? Yeah? Okay. Now, the thing that shows me what the cycle structure is the question when does this cycle end? how do I write cycles here? The cycle ends whenever the last element is then taken to the first element. So for S, for example, a cycle will close whenever I is taken back to itself. So this thing, I, when S is applied on it, will go to S of I. This will then go to S of I. And let's say that after M steps, we will have S of I M times equal to I. Then this cycle closes. Now, when S of I is equal to I, this cycle also closes. Because we started from T of I, and we go up to T of S some power M of I, which is just T of I. So this cycle closes at the same number of steps. Okay, maybe this is more detailed than what you needed. But we still have some time to talk about infinite groups. Okay, the first example of a group of infinite elements is the group of rotations in 3D space. What is the definition of a rotation? Is an operation on a 3 vector. R goes to R prime, let's call this R acting on R. That does not change the length of the vector. R squared has to be equal to R prime squared. This is the definition of a rotation. So what does this mean? It means that the transpose of the vector times the vector should remain invariant. Sorry. And using this notation, this thing is just transpose of R times the transpose of the operator R. So here R and R transpose are 3 by 3 matrices. So in order for R to belong to the rotation group, R transpose times R should be equal to the identity matrix. In other words, R has to be a 3 by 3 orthogonal matrix. And this gives us the orthogonal group in 3 dimensions, O3. Okay. An equivalent an equivalent way to define rotations is that they leave the metric in the three-dimensional space invariant. Remember yesterday we talked about metrics and scalar products? Let's see how this applies here. So any scalar product of two vectors, x times y, should remain invariant under rotations. Now, if x goes to what do we mean by this, first of all? We mean the ith component of x times the yth component of j times our metric gij. Now, under a rotation, xi goes to rik xk, and yj goes to rjl xl. And if we require this to be invariant, this has to be equal to xk xl rik rj jl dij. And now if we just relabel our indices, we see that the metric remains invariant. In other words, gij is equal to rki rlj gkl.
So shouldn't yj go to rj lyl?
Where are you referring to?
Why do you have xkxl?
Okay, so if I am allowed to relabel my dummy indices whenever I want, so let me call this.
No, but I mean, you have xy and then you have xx.
Oh!
And the
Yeah.
second row, third row.
Sorry?
Y goes to R
Yeah,
on
on the left, the last line.
Okay, I cannot write x's. Just answer all the questions. Oh, sorry, y's I cannot write. Anyway, so this means that the metric remains invariant. This can also be written G equals the transpose of R times G times R. So rotations leave the metric in Euclidean space invariant. And we will see that rotations in Minkowski space or Lorentz transformations will be defined so that they leave the Minkowski metric invariant. Now, from this relation, we see that the determinant of R squared has to be equal to 1, which means that the determinant of R can either be plus or minus 1. If we choose the determinant to be plus 1, then we've got the special orthogonal group, SO3, which is the same as O3, but it actually does not include reflections. Okay? And if you want to talk about conjugacy classes of SO3, you will see that these are rotations of the same angle, but about different axes. This is just one thing you can check yourself. So as I said, SO3 gives us, O3 and SO3 give us rotations in the real Euclidean space. What if we want to study rotations in Hilbert spaces? Then we need complex matrices. And then we are talking about the groups UN or SUN. So what is the group UN? It's the group of all unitary n by n matrices. And if we take some state vector in a Hilbert space and we apply a unitary transformation on it, we see that the measure of psi remains invariant as long as U dagger U is equal to 1. So as long as psi has n components, psi 1, psi n, U has to be a unitary n by n matrix. And we have again some options for the sign of the determinant of U. Since we are talking about complex matrices now, this relation means that the norm of the determinant is 1. Or in other words, the determinant of U is just some phase. If we choose the determinant to be +1, then we have the special group SUN. Okay. Can I write the most general SU2 matrix? This will be a 2 by 2 matrix. And let's assume it will have 4 complex components. This will be U. You can easily check that the requirement that U dagger U equals the identity is equivalent to this set of relations. Norm A squared plus norm B squared have to be equal to 1. AC star plus B star should be equal to 0. And norm of C squared plus norm of D squared should be equal to 1. And if you solve these equations, you will get that D should be equal to A star times some phase. Let's call it I theta. And C should be equal to minus B star times the same phase, which means that our matrix can be written A, B, A star e to the I theta minus B, minus B star e to the I theta, and here A star e to the I theta. And the determinant now of U is just A squared plus B squared times this phase e to the I theta. So as long as as long as we want U to be an element of SU2 and have determinant 1, this phase theta has to be 0, and A squared plus B squared has to be equal to 1. So the most general SU2 matrix can be written as A, B, minus B star, A star, where A and B are complex numbers. Okay. Now, A and B are complex numbers, so let me write A equals x plus iy and B equals u plus ib. Sorry, the requirement is also that A squared plus B squared equals 1. Well, if I plug this in here, and then I go and calculate again the determinant, it's not hard to see that this takes me to x squared plus y squared plus u squared plus v squared equals 1. Now, if you treat x, y, u, and v as coordinates in a 4-dimensional space, this is the equation to describe a sphere in that space. That would be a 3-dimensional surface, S3. This is why we say that SU2 has the topology of S3. Now, another interesting thing is the relation between SU2 and SO3. So I claim that there is a homomorphism between SU2 and SO3. And I think that a nice way to say this is to take some 3-dimensional vector, x1, x2, x3, and associate it to a 2x2 complex matrix, which I call X. And I define as the sum of the xi's times the Pauli matrices sigma i's. Sigma 1 is 0, 1, 1, 0. Sigma 2 is 0 minus I, 0. And sigma 3 is 1, 0, 0. Minus 1. So X will be a 2-dimensional, a 2x2 complex matrix, X3 minus X3, X1 minus I, X2, and X1 plus I, X2. Now, you can check that the Pauli matrices satisfy a specific algebra, and this is one of the nice relations you can write from this algebra. The product of sigma I times sigma j is equal to delta ij times the unit matrix times the unit 2 by 2 matrix plus I times epsilon ijk sigma k. So let's look at the scalar product between two vectors x and y. What do I want to solve? Okay, so I want to find a way to describe this scalar product using my 2 by 2 matrices. So I'm going to write the matrix product between x and y using those relations. This is xi sigma I times yj sigma j. And now I know that this is xi yj times delta ij times the unit matrix plus I epsilon ij k sigma k. This is equal to the scalar product of x and y times the unit matrix plus I xi yj epsilon ij k sigma k. So my scalar product appears in here. Now, if I take the trace of this relation, the trace of the identity is 2. So this is 2 times the scalar product. And then it's not hard to see that the trace of all the Pauli matrices is 0. Which means that the scalar product between the vectors x and y will stay invariant as long as the trace of the product of these two matrices stays invariant under some operation. So I broke it. So now, what if we act with an SU2 operator on the matrices x and y? X will go to u x u dagger, and y will also go to u y u dagger, which means that, sorry, let me move this back. Which means that the product of the two matrices will turn into ux u dagger uy u dagger. And as long as u is a member of SU2, this is just unity. So this is uxy u dagger. And it's not hard to see that the trace of the product will go to the trace of uxy u dagger, but in the trace I can rotate matrices. So this is just the trace of xy, and it is invariant. Which means that the scalar product of the two vectors is also invariant. Which means that I can find a map that takes me from an SU2 operator to an SO3 operator, because the scalar product is invariant. So the two groups are homomorphic. And if you look at it more carefully, and I think I will ask you to do this in the tutorial later on today, you will see that the map from SU2 to SO3 is 2 to 1, which means that two elements of SU2 are mapped to the same element of SO3. This is why we say that SU2 is a double cover of SO3, and we write SO3 is SU2 by Z2, which is just a change from +1 to -1. And if you want to use the topology of SU2, SO3 will have the topology of S3 divided by Z2, which means that SO3 has the topology of a half sphere only. You will only get half hemisphere. I'm not very good at drawing, but SO3 has the topology of only an upper hemisphere.
It's also not simple.
Yes, but sorry, you have to say this again from louder and from the beginning.
Projective space in 3 dimensions, which is basically the free sphere, so S3, where you identify the antipodal points. So you identify point X with -X.
Okay.
It's three sphere with antipodal points identified,
Okay.
which is not the half sphere, but it's a.
But if you
If you
take this
identify-
quotient, it's guided indeed the same, right?
Any other questions? No? Yes.
So, I'm not, like you wrote X, Y, and then I guess X multiplied by only matrices, but Y.
Why I wrote this as
Yeah, I'm just not sure what the operation you're trying to do is.
basically I'm trying just to map somehow a 3-vector to a 2x2 matrix so that I can act on it with an SU2 matrix. And then I want to show that as long as you have mapped them this way, then the scalar product of 2 vectors would remain invariant under the same operation. But I haven't given you here the map from SU2 to SO3. I haven't really given you the way to go from one to the other. I just think this is a nice way to look at it. But
So that X and that Y are both matrices associated with
with vectors. Yeah, so Y would be another vector with coordinates yi. Yeah.
But one question, but the map is simply that here you are using 2 matrices and you use for the SO3 one matrix, so this will be the map, no? Like the transformation in SU2 goes with 2 matrices. So if you put the minus sign in these matrices, it doesn't matter for the R, and then that's what.
Yeah. I mean, yes, you will see that it doesn't matter if you change the sign of U because you get back to that exactly. You see it from here. Where did I write it? here, basically, as long as you change u to minus u, you get exactly the same thing, so it doesn't make a difference. Okay, so next week, I guess we will be talking about the Lorentz group, most likely, but it also depends on what we do with Freddy on Monday and Tuesday. Just one thing about tomorrow. You will be sent a schedule for the talks tomorrow. As we already said yesterday, please make sure that you have given us your full presentation files before your session actually starts. And you will also be sent some instructions on feedback later on today. You will be asked to give feedback for some other people. Each one of you will be assigned to specific people so that not everyone has to give feedback on everyone. And you will do that electronically. But it's worth having a look at the feedback forms tonight so that you know what we kind of expect from you so that you can prepare better. And then you're also prepared on how to evaluate others.
Don't give feedback before you hear the talk.